Here you see the PhET photoelectric effect simulation. It's a very realistic simulation. If we were going to do this experiment in the lab, you wouldn't see the electrons coming off the plate, you wouldn't see the light beam, but you would be reading values for current and potential difference just like you will on this computer simulation. Now, some of the buttons on the simulation, you have intensity. This is for our light source, where we can go up to 100%, which is the brightest, or down to 0%, which would be turned off. One of the things you're going to explore is the differences in these photoelectrons that come off of the metal plate when the light shines on it based on the intensity of the light source. So these electrons would be coming over in the real lab, but you wouldn't see them. So we can adjust the intensity and see how that affects our situation. We also have a slider for the wavelength of the light source. Now, this wavelength varies all the way down from 100 nanometers up to 850 nanometers for our sodium target. You can change your targets by using the drop-down button for the target. So since velocity equals frequency times wavelength, if the speed of light is 3 times 10 to the 8th meters per second, and we have a wavelength of 629 nanometers, then the frequency of this light would be 3 times 10 to the 8th meters per second divided by 629 times 10 to the minus 9 meters. That would give us a frequency in hertz. So you take the speed of light in a vacuum divided by this wavelength to get your frequency. As you adjust the frequency, and by moving the wavelength slider, you may or may not see photoelectrons emitted. One of your tasks is going to be to find the cutoff frequency, or the boundary or barrier between if the wavelength is too low or too high, it either will or won't work. So we're looking for a cutoff frequency. What is the highest frequency or the lowest wavelength that will make this work? So you'll move the slider until you don't get any photoelectrons coming off. Well, it's kind of hard to precisely pinpoint the slider values, so anytime you need to, you can click on it and type in. I can go with 189, or I can type in and make it 191. So remember, besides moving the slider, you can type in. You're also going to be looking at what we call the stopping potential. Since these electrons are coming off and they're negatively charged, the plate over here, we can adjust its potential to either attract or repel those electrons. That voltage that repels the electrons, which will need to be a negative voltage, is known as the stopping potential. So when these electrons come off, what's the smallest negative value that would repel them? So obviously negative 1.8 volts is keeping these electrons from making it over. But if I reduce that voltage, they'll start coming a little bit farther, and it looks like they're making it all the way over, so I'll slide it back to say negative 1.7, and you can see it's really difficult to pinpoint this, so by clicking on it and typing in a value, you'll be able to more precisely get readings. So now you can see at this voltage, they're making it just over, but they're not being captured by it. If I want to try, well, it works on negative 0.8, what about 0.79? Make it a little less powerful. I can type that in and watch what happens. And it caught it. So they're actually making it, so it looks like that negative 0.80 volts would be our maximum or our stopping potential. So the current shows 0 at a range of voltages here. So you really want to pinpoint that voltage to get the precise cutoff value. You're going to be trying a couple of different targets, and you will also use an unknown. The data that you collect will allow you to find the value known as Planck's constant. You'll explore how the intensity affects or doesn't affect the photoelectric effect occurring and the energy of the emitted photoelectrons. You'll see how wavelength does or doesn't affect whether or not the photoelectric effect occurs, and if it does or doesn't affect the stopping potential, which is the energy of those emitted photoelectrons.